everyone, this is Dr. O. In this video, I'm going to explain similarity measures. Similarity measures we use to gauge whether a group of observations are similar or dissimilar to one another. These measures are important for understanding both supervised and unsupervised techniques. For instance, K-nearest neighborhoods, a supervised technique, uses similarity measures to identify similar observations. An unsupervised technique, cluster analysis, similarity measures groups observations based on similarities. So here on the screen you see three observations, and these three observations has x1 and x2 coordinates. x2, as you know, it's the y-axis and x1 is the x-axis. And this figure plots these observations. You can clearly see that observations 1 and 2 are closer to each other, implying they are similar to each other. Also, you can see that observation 3 is dissimilar from observations 1 and 2. Therefore, by visualizing the data, you can find similar and dissimilar observations. However, if you have a big data, just visualizing is not going to be enough to find similar and dissimilar measures. In this section, I'm going to present a more formal way to measure similarity among observations for first numerical variables and then second for categorical variables. Let's start with Euclidean distance. Euclidean distance is one of the most widely used measures for evaluating similarity with numerical variables. It is defined as the length of a straight line between two observations. So if you have k numerical variables x1 to xk, the distance between two observations I and j is calculated with this formula. Let me show you how to calculate Euclidean distance for the observations 1, 2 and 3 we have on the screen. We are going to find Euclidean distance between all pairwise observations. So we have pairs 1 and 2, and then we have 1 and 3, and then we have 2 and 3. Let's write the formula for Euclidean distance. In square root, we get first x1 of the first variable minus x1 of the second variable, and then square. Plus, get x2 of the first variable minus x2 of the second variable, and then close the parentheses and square. So here x1, 1 is 3. In square root, x1, 1 is 3. Minus x1, 2, 4. Square plus x2, 1 is 4. Minus x2, 2 is 5. And then square. In square root, 3 minus 4 is minus 1. Plus 4 minus 5 is minus 1 and square. So that is equal to, in square root, 1 plus 1, or in square root 2, which is close to 1.41. This is the Euclidean distance between the observations 1 and 2. Let me show you 1 and 3. So for 1 and 3, x1, 1 minus x1, 3. That means take x1 for the first observation and then take x1 for the third observation and square. Plus x2, 1 minus x2, 3 to the power 2. So x1, 1 is 3 minus x1, 3, 10. And these are all in square root. Plus x2, 1 is 4 minus x2, 3 is 1. That is 3 minus 10 is minus 7 to the power 2, plus 4 minus 1 is 3 to the power 2, which is equal to, in square root, 49 plus 9, which is in square root 58, or close to 7.61. So I show manually how to calculate Euclidean distance. We can easily use Excel to calculate Euclidean distance for us. So we start with an equal sign, start with SQRT, and then open the parentheses, open another parentheses, and then select x1, 1 minus x1, 2. Close the parentheses and square. Plus, open the parentheses, x2, 1 minus x2, 2. Close the parentheses and power 2. and close the parentheses for square root and then enter. And if you want to find Euclidean distance between 1 and 3, then again square root function, open the parentheses, and one more time open the parentheses, x11 minus x13. Close the parentheses to the power 2, plus open the parentheses, x21 minus x23. Close the parentheses, square, and close the parentheses for square root, and then enter. And now finally, we can find the Euclidean distance for 2 and 3. One more time, open the parentheses. This time, x12 minus x13 to the power 2 plus, open the parentheses, x22 minus x23 to the power 2, close the parentheses, and then enter. Here are the results. Using Euclidean measure to gauge similarity, observations 1 and 2 are the most similar with the shortest Euclidean distance of 1.41. Observations 1 and 3 are the most dissimilar given the longest Euclidean distance of 7.62. Next, I'm going to talk about the Manhattan distance. Manhattan distance is the shortest distance between two observations if you are only allowed to move horizontally or vertically. Referring to the city of Manhattan, if you have visited Manhattan, you realize that the city is laid out in square blocks. The Manhattan distance between 2 points is the shortest path for a vehicle to travel from one point to another in the city. For a data set that we have k variables, the Euclidean distance is found as follows. In absolute terms, x1i minus x1j plus x2i minus x2j, and it goes until xki minus xkj. Let me show you how to calculate Manhattan distance using the three observations we have here. So we have three pairs, 1, 2, 1, 3, and 2, 3. We will calculate Manhattan distance between all paired observations. Let's start with 1, 2. Take x11 minus x12 plus absolute value. Take x21 minus x22. So x11, x1 of the first observation is 3, minus x1 of the second observation is 4 in absolute value, plus take x2 of the first observation 4 minus take x2 of the second observation 5, again in absolute value. This is minus 1, this is minus 1. You know that absolute value changes negative coefficient to positive, so this is 1, this is 1, so Manhattan distance is 2. Let's do for the second pair, 1 and 3. x11 minus x13 plus absolute value x21 minus x23. So x11 is 3 minus x13 is 10 plus x21 is 4 minus x23 is 1. That is here negative 7 plus 3, so that is 7 plus 3, 10. So the Manhattan distance for the pair 1, 3 is 10. So equal sign, absolute function, x11 minus x12 plus absolute value, x21 minus x22. And now let's do that for 1, 3. Absolute function, x11 minus x13. Absolute function, x21 minus x23. And now here, between 2 and 3, x12 minus x13 plus absolute function x22 minus x23. So here are the results. Like the results found using the Euclidean distance, observations 1 and 2 are the most similar based on the Manhattan distance. Observations 1 and 2 are now equally dissimilar to observation 3.